Today, we're going to have the director of the Concrete Sustainability Hub, Franz Olm, going to present to you some research that he's been working on with a diverse set of collaborators on ways in which we can improve our infrastructure using crowdsourced data. And with that, I'm going to turn it over to Franz. But one last reminder, if you have questions, we have everyone on mute to help keep background noise down, but we'd love to hear your questions. And there's a question and answer box in the lower right of the WebEx. And when Franz is done talking, I'll read him some of the questions we get, and then he'll be able to answer them. So with that, take it away, Franz.
Thank you very much, Jeremy. My name is Franz Olm, and I'm here professor at MIT. And this work is more a starting point for a project which I hope I will be able to convince you to participate. It's the subtitle of it is "What can you do with your smartphone to make our infrastructure great again while addressing climate change?" And this work was done in collaboration with my student Jake Roxon here from MIT at MIT, and a student from Harvard, Shahd Nara, who is also part of the Carbin team, and I will say more about it later. A graduate student from UMass Dartmouth, Meshkat Botshekan, Erfan Asaadi, former postdoc at UMass Dartmouth of Professor Arghavan Louhghalam, and Professor Mazdak Tootkaboni from UMass Dartmouth. To start with here is why would I ask you to take some time out to address this issue? The motivation is pretty clear. We look at greenhouse gas emissions by different economic sectors and realize that the transportation sector makes roughly 1/3 of it. And if you break this transportation sector up further down with light vehicles, medium, heavy vehicles, you see there's a substantial amount of greenhouse gas emissions that relate to the transportation sector. The question which I actually want to address here is how does the state of our infrastructure affect greenhouse gas emissions, fuel economy, and so on? And more specifically, I'm looking here at pavement vehicle interactions. Pavement vehicle interactions make 72% of the overall life cycle of pavements. It is due to roughness, dissipation due to texture, and dissipation due to pavement structural and materials. Specifically, what I'm looking today about is on roughness. Now, in a larger context, I want to raise the question here, let's say, are we doing the right thing for our infrastructure, or are we just living out the glorious time of the 1950s when the administration of President Dwight Eisenhower, brought forward $25 billion in order to start the current federal highway system, which, by the way, would be today $235 billion, which, of course, is much more than when we look at the current administration's allocation of funds of on the order of $47 billion in the Transportation Act, the so-called FAST Act. It may thus be not surprising that the American Society of Civil Engineers, in its infrastructure report card, gives the infrastructure, the road system, a grade D, with the following notations. There are about $160 billion wasted in time and fuel. 1 out of every 5 miles of highway pavement is in poor condition, and our roads have a significant and increasing backlog of rehabilitation needs. So the question which I ultimately want to answer, not today, but start actually the discussion, how can we address this? Where would you put your dollars to revitalize our infrastructure while addressing climate change? In fact, that's what I want to do. We may be able to find out if we use smartly our smartphones, I want to convince you that we will be able collectively to provide quantitative data for decision makers, e.g. for highway bill, but also for local bills, assist cities and communities to reach their climate goals, for instance, their CO2 emissions, value infrastructure for sustainable growth of our society, which has been more and more put on the back burner, that there's a value to infrastructure, and ultimately empower citizens to contribute and take charge of our built environment. The outline of my talk will be 4 points. I need to go a little bit into the background here in order to show you how, by means of smartphone, we are able actually to predict roughness, look on excess fuel consumption, able to predict, to be quantitative. I want to introduce you to an app which my students, but particularly Jake and Shahd, developed. It's called Carbin. I want to show you what this can do for you, and then bring it all the way from an individual measurement with one phone to crowdsourcing, and introduce to you the potential of the Fix My Road project, showing network applications, vision, impact of crowdsourcing before coming to conclusions and timelines. So as a background here is the following. A common measure of to quantify ride quality is the so-called International Roughness Index, IRI. It has been introduced by the World Bank in the 1980s and then quickly adopted all over the world to quantify ride quality. Now, what is this roughness here? Well, the roughness basically here is the movement over the average movement of your suspension system in your car, not in your car, but for a reference car, the so-called golden car here, over a distance length. From this measurement at a given speed, V0, which is 80 kilometers per hour. With this measurement, which can be done here, for instance, by lasers, or here one can classify roads in different ways, as long as this IRI measurement is given in meter per kilometers or millimeter per meters, or in the US in inches per mile. Here's the conversion factor, 1 meter, 63 inch per mile. It's basically airport, new pavements, older pavements, maintained unpaved roads, damaged pavements, rough unpaved roads, etc. The value here of new pavements could be corrected a little bit more downwards here. New pavements today can be easily be done with an IRI value of 1 or 63 inch per mile delivered. So this would be, if you measure it, these measurements are not cheap. They are actually only done typically for the highway system, and not always for all federal roads. They are barely done in any city for cost reasons. So how would we actually know how this roughness actually introduces excess fuel consumption, environmental impact, etc.? So for this reason, let's say what we do here, actually, I need to, for those who are less familiar with the mathematical techniques of Fourier transforms, is what I mean by roughness actually here is what a surface may look like if you were to measure here the roughness of a certain profile of the street. Now, if you decompose this signal in the driving directions into different wavelengths here, and you have here K, so wave numbers actually here, so from large numbers to small numbers here, well, then you can actually represent this here as a spatial, in terms of spatial frequencies here, and we are wondering how much these frequencies actually affect the fuel consumption. For roads, typically, when we look at roughness in terms of IRI, we look for wave numbers here between 0.35 meters and 90.9 meters. For smaller, even smaller wave numbers, this is something which affects the texture of the tires, which also introduce additional fuel consumption. So what we then actually do to classically way to infer IRI from measurements here as an alternative here to measuring actually how much in time your suspension system moves, we actually use the following form. Here's here's this transformation as a function of the spatial frequency. It's called power spectral density here. Power spectral density, as you see here. In essence, as you see, let's say for the spatial frequency here, this is for a large wave number, so the 90.9 meters, and here is for low meters. And this decays here typically for pavements in a power fashion here, with W being so-called waviness number here. And if we have this measured roughness power spectral density and multiply this here by some response function, so here's this roughness to which your tire is subjected here. We multiply this here by some response function and integrate this here in some way. We are actually able to calculate this IRI by just knowing here these relations plus these known reference golden car properties. Well, how does roughness lead to excess fuel consumption? Well, you immediately understand this if your suspension system is moving up and down. Each time when it moves up, it's the speed to the power 2 times some damping coefficient here will lead to an energy dissipation. Energy dissipation means the loss of energy which we put in the system through the fuel into our cars, and then we can calculate actually here the energy dissipation or the excess fuel consumption that results here from the suspension system. We may want to add as well the energy dissipation that may occur in the tire, but I will today only focus on this part, on the suspension system. There has been a long standing work actually done by Professor Shahd here in the United States in order to identify what is sort of the excess fuel consumption percent in function of this measurement, this IRI value here, and depends on the speed, etc. These are clearly, as the rougher it is, the more excess fuel consumption we consume because we don't like to have a rough ride. So this all has to do with ride quality, but here it comes with excess fuel consumption. Such an excess fuel consumption also leads here to CO2 emissions because each unit of gasoline or diesel spent in our vehicles leads to CO2 emissions. In addition to CO2 emissions, one can think about particle matter, NOx, and many other things. So more specifically, I'm very much interested in identifying not only the amount of fuel which we spend in excess of just running our motors at a given speed, but this excess fuel and environmental impact that results here from the roughness. In fact, one can analytically determine this here. Analytically, if we have a measured roughness, but then we multiply it again here with some function that is where the vehicle properties come into place, but this is now your vehicle, not a reference vehicle, which is used classically for IRI. We actually are able to determine here the excess fuel consumption, the energy dissipation in the suspension system. So a key input here is this roughness value, and here this and the vehicle properties of your car, if they are known. Now, how does that relate to smartphone measurements? Now, in a smartphone, if you consider it like this, all smartphones today have acceleration inbuilt, and so we can actually record in time the acceleration of a smartphone, specifically the vertical acceleration of the smartphone. We can then relate this acceleration here in a similar fashion here to, on the one side, this roughness characteristic power spectral density of the road on which we are driving. That's, of course, dependent on the geography, and multiply this here with the appropriate properties that relate to your car. But what we would need for that here is we would need to know what are the properties of your car. The theory is now relatively well established, so it should be pretty much straightforward in a forward application if this was known to determine how much energy we consume. However, obviously, we don't know your vehicle properties, nor do we know what the roughness properties is. We don't have a laser profiling the road. So the question here of this approach actually consists of taking here smartphone records, the acceleration of the body mass, so a phone fixed smartphone attached to the body mass. We need the speed, and we need the position in order to map it. And the output, in return, what we would do then here by an inverse analysis is to determine the vehicle properties, the roughness, power spectral density, and of course the International Roughness Index here, which is used for many other applications, particularly for maintenance, the excess fuel consumption, environmental impact, and ultimately the mapping. Now, this may sound so straightforward that one needs to go backwards and realize, let's say, well, this should have been in the books for quite some time. Well, when you make a literature search about that, what exists, actually, you have basically three types of approaches that are in the literature. So one of the approaches is sort of an ad hoc engineering approach, with the idea that if you have an acceleration, you integrate the acceleration twice. You obtain some displacement, and eventually you can relate this to roughness. Of course, if you do this, you assume basically that you drive a rigid vehicle. So that can be but an extremely rough estimate of the system. Actually, this type of technique came from the pothole bump approaches, which there are many out there, which register the occurrence of potholes in the street by means of these acceleration. But it has been applied also to IRI. The problem here that this is a rigid vehicle. Then there are many correlation approaches out there. They actually go all back, I would say, to a patent which Google brought forward, where you correlate something to the IRI, which you measure from the acceleration, and hope that the correlations will work. The problem of correlations are, of course, that they're not necessarily transferable unless you have artificial intelligence and etc., which learns permanently the entire system. So you need to calibrate already your artificial intelligence in a way in order to have the answer, which of course limits this approach. In addition, it does not consider all the fine things which actually one can do with the accelerations. Finally, there's a team actually in Italy, specifically, who has used random vibration theory, which I just showed to you. They consider actually the roughness power spectral density. To some extent, they have a limitation to the slope here, but it's the idea of a low-pass filter which they apply there here. But they find that it was speed that have some speed dependency in their approach. They use, of course, acceleration. They do not consider your vehicle properties, so it's not transferable from one vehicle to the other, because they consider golden car properties, actually, so a reference car, which they overlay on your properties. And finally, because of this limitation, they determine some roughness or index road classifiers, but not the IRI per se. And none of these, of course, address here the environmental impact which comes for here. Nevertheless, I advise you to go to this website. Let's say it's pretty impressive what they have been able to achieve by means of smartphone measurements. But because of this here, we wanted to take it on with this approach, to bring all these different elements here together with Carbin, where we had considered the stochastic process of it, the random vibration theory. Vehicle properties actually need some probabilistic inverse analysis. Here, IRI classifier from random vibration theory, and the environmental impact basically from elementary thermodynamics. That's what we call the Carbin approach. which is in this app. In fact, it started as a student project. It's currently in a version of as a research tool, and but has all the potentials to move into the startup technology as we try to scale up these type of measurements for a large-scale application of this app. So how does this work, actually, this Carbin app? So you have the classical situation: a smartphone is mounted in a fixed position inside the vehicle. So that's important, that it shouldn't move too much inside the vehicle. There's a Carbin algorithm which we developed based on this probabilistic inverse analysis, which my colleagues at UMass Dartmouth actually developed to extract road quality, vehicle properties, and excess fuel consumption information. In order to achieve this here, the smartphone actually sensors collect the speed, GPS, vibrations at a frequency typically 100 per second. That's 100 hertz frequency. And then finally, with this information, we can use this data to monitor fuel consumption, quantify environmental impact of roads in terms of excess CO2, NOx, environment, and particular matter. Now, let me walk you through some measurements. Here's a measurement which I took one weekend driving back from Western Mass. It's a measurement which I took over 30 minutes. So you see here, typically what it measures is the speed, actually the speed from the GPS record. You see these spikes here actually come from the fact that the GPS system takes some time. Of course, you know, this is the frequency of the recording per se. However, when we analyze here the roughness and the fuel consumption, we put ourselves in 30 seconds time windows, which in order to have data to evaluate the roughness-induced fuel consumption. A second measurement is the acceleration. You see, let's say there's a lot of measurement, 100 hertz, so 100 values per second that are recorded by the smartphone, put on the dashboard. Now, what do we do with this data? So, as I said, we have this moving time window which moves with a certain delta t forward, roughly all second here, and this 30-second time window, we take this acceleration, we put this in, make a Fourier transform of it, and to determine the acceleration power, spectral density. Then we use, so in red here is a model PSD, which is obtained actually by application of a probabilistic inverse analysis, which is pretty important because otherwise the problem is ill-posed in order to obtain here the model response. So in blue is the measured one. In typically measured response here is the model response here in red. In addition, we determine here this roughness PSD. So that's really, let's say, how we infer from the acceleration the roughness PSD of the road we are driving on in this 30-second time window here. And typically two parameters we're interested in. One is this waviness number, the slope. You see it enters here, and on the other side here, the magnitude of it, which is this quantity, which is called unevenness number often. With these two quantities, we are able to determine the roughness, the fuel consumption, etc. Forward. But as I said, let's say we are able to determine the vehicle properties using this probabilistic inverse analysis. And because it's probabilistic, what we obtain actually a distribution of properties. So, for instance, the vehicle frequency, resonant frequency, here you see here a typical distribution. Compared to the prior art, which uses the golden car, you see, let's say, the car with which I was driving, which was a Volkswagen Jetta 2017, really is quite far off from the properties which have been used, which are classically used in the system. Here's an interesting quantity, which is actually the stiffness ratio between the tire and the suspension system. The golden car property is sort of around 11-ish, 10.3 actually to be more precise. And again, you see, let's say I'm quite off with my car from this value. Why does that matter? You know, if I have the statistics information of the vehicle and I store this and continue analyzing this here, if there's a statistical significant shift of these stiffness properties, I could immediately identify there's a tire problem or some problem with my suspension system, etc. Similar, you know, is the mass ratio between the mass of the tire, the lower part, and the body mass. So that's a little bit more diffuse, but there's chances here that we are able to determine the vehicle mass directly from this here. And the other one is the suspension damping ratio, which you also see that compared to the golden car, a certain distribution of the vehicle here, which would tell me if a shift occurs that there's a problem with my suspension system. Now, in terms of roughness, you see here the output. What you then obtain, of course, with this smartphone would be for each 1 second move. So you see here the resolution of it. You get the roughness here, and you see that there is some pattern here. I put this here in meter per meter, but note this is 10 minus 3, so this is meter over kilometer. If you forget this quantity, meter per kilometer is the standard actually in the ISO standard here in the United States. We use you can transfer this here to 63 inches per mile. Note that 1 meter per kilometer is basically a new pavement here. So you see that we are here actually at quite variable IRI. In fact, I took the work, this is from Western Mass, and looked at the mass.web page in order to identify when has there been some work done recently. And actually this part here was resurfaced in 2008, 2009, so some 10 years ago. And you see, you see still a little bit of an effect, but it's already wearing off very quickly. Also, the resurfacing that happened in this part in 2012, even though it's a little bit better than the rest of it, let's say starts wearing off. And of course, this is a measurement, just one measurement. But if there are sufficient vehicle driving over this part, you can continuously monitor here the roughness of the road. In fact, what you can look then also there, look at the statistics here. So, for instance, here in terms of the roughness here, you see there's a certain distribution. If you want, you can take the mean over this 10-mile stretch here. And in essence, you identify, well, this is an older pavement, and then this can be a guide for the DOT to take decisions when to intervene, either locally or for this entire segment, to reduce by means of resurfacing the roughness. But that's a classical approach. The new approach actually here comes to link it here to the energy, to the excess energy consumption due to this roughness, because we like a good ride. Please notice the log normal part, as you would expect if all of the other phenomena are normally distributed, well, then you obtain from the cumulation a log normal distribution here of this energy consumption along the stretch. So this allows us to address the following issue, that IRI induces excess fuel consumption, CO2, NOx, PM. And of course, how much is it? Well, you know, if we can plot this, of course, along the way. But what is more interesting here is, in essence, to bring together the roughness and, to address this here, to bring together the roughness and the dissipation, to plot the dissipation, excess fuel consumption, and the roughness here of the system. And clearly you see that this roughness leads to an energy consumption. It's not really a linear relationship, but here you get, you have access to this quantity in real time while driving with your Carbin app. Now, how much fuel is this? You can integrate this, and of course, you know, and you will realize for this relatively short stretch here of Route 2 highway system, you basically, it's not much fuel that we spend. It's 30 milliliters, which is roughly 2 to 3% for my highly fuel economic Jetta 2017. You can translate it in 70 grams of CO2, so it's not much actually for me as an individual, at least for this small part, just 2 to 3%. However, So in fact, if you just plot this here, you see here this that's sort of the amount of what 30 milliliter of fuel would look like. But if you take this for the entire road, so for this entire segment here, and consider the average annual daily traffic for this segment, you actually realize it's not that little. It actually amounts to 1 barrel of gasoline per day and roughly 280 kilogram of CO2. So per day, if you then scale this up for the year, you see these numbers become significant. Just another application, because I have phone here from Massachusetts. The Mass Pike is sort of the flagship of the connection between Boston on the one side and Worcester. So a friend of mine drove yesterday from MIT visiting me to Worcester, and I asked her to measure the roughness and send me the data. So what you see here, the Mass DOT maintains it. Okay, I have put this now here in inches per mile for the use of people who are more maybe familiar with the inch of mile. You see, we're here sort of in the so around 150 to 200 inches per mile. So we know that this is not far away from a need of redoing this here from a roughness perspective. Again, let's say because it's a highway application, the excess user costs actually in terms of petrol are small compared to the engine power cost, but again, it is critical when aggregated, i.e. when we go at state level, federal level, and need to address this here, there 2, 3, 4% make all the difference, because that's something which we can influence by appropriate maintenance schedule and the right choices of the segments which are critical for reducing the environmental footprint and the fuel economy. But this was just out of highway application. But what about in inner city application? So I show you here a way which I drove one evening from Boston over to Cambridge. Most of the measurements here are in Cambridge. Here's Massachusetts Institute of Technology, so into the heart of Cambridge. See, the speed, of course, here is much lower, right? We're talking about sort of 20 to 30 mph with a little bit of luck here. But the IRI is significantly higher than what we are used to. So remind you, it was sort of around 3 on the highway here. We're talking about here values of 7 or even higher than this here for in the system. And the fuel excess fuel consumption accordingly is also much higher. In fact, well, first of all, let me say something about resolution. So this is around Inman Square here in Cambridge here, just to give you an idea about this resolution. So if you take here a street here, this is basically a block level. You see here the measurements which are done there, extremely consistent here. You see here Hampshire Street actually is in a better state, was redone a couple of years ago. Prospect Street, this part here is also consistent value, but much higher, so that may need some retrofitting in the future. So that's sort of the spatial resolution which you get out with your smartphone combined with the algorithm. Well, there's also some difference you can look at, so left and right wheel, because there's not only one roughness, but the right side is often more deteriorated, particularly on this path. So we had measurements done with 2 phones together with my daughter, where we saw that there are parts of it where the right wheel is subject to higher roughness than the left wheel, and which allows us then to integrate that here into the excess fuel consumption. But first of all, let's say, where are we with this roughness? So if you look at the values, we're basically talking about that the state of the road system, at least this part here in Cambridge, is basically the equivalent of a maintained unpaved road. And I think anybody who ever drove in Cambridge knows that there are issues with the system. So it means that these need another level of maintenance or choice of budget allocation just from a roughness perspective. But why does that really matter? It actually matters because of of the excess fuel consumption. So just to give you an idea, this was 2.5 miles. So it was 1/5 of the way which I showed you before, which I drove on the highway. But I have 3 times as much fuel consumption. So for 1/5, I have 3 times as much excess fuel consumption for my vehicle. So that amounts to 3 to 5%, because we all know that we get much less miles per gallon in a city. And which means then, if I just to give you an idea, that's a full cup here for 2.5 miles here, which means the CO2 impact, but also the other environmental impact factor in a city are really detrimental for the quality of the air, etc. And then really you realize actually that for this small segment alone of some 2.5 miles, if there are at least 1,000 vehicles per day, because that's one of the ways into Central Square in Cambridge, well, that this comes basically also to a barrel per day, and that's a very dense settled population. So then, of course, you can look in vehicle properties again. In a city, you obtain similar type of properties, and they are quite different from the approach previously used using the golden car properties. So you can then check whether there's equal mass distribution, left, right, etc. So these are interesting things one can do with the outcome of it, let's say, about vehicle properties of the system. Also, Jake actually drove this year with his car. I forgot what it was. I think his brother's car here. And as he sent me the data, actually here, I made the analysis. I told him, you have a problem with your car, particularly with this first run here. And I asked him, was this an outlier or do you have problems? Soon afterwards, he came back and said, well, he had to redo the steering system. Had I analyzed this before, I could have shown him simply by looking at the resonance frequency from the before the repair and after the repair, which I didn't know from this distribution. I could have told him more quantitatively to use this problem. It's not in terms of mean values. This is higher statistics in order to analyze the quality of the vehicle properties. So just to summarize this here, what checklist? So we looked at speeds. Recommendably is greater 15 kilometer per hour. Non-stationarity is something which affects the output. It's what we call the yield, how many data points you get along a route. The vehicle type, we checked with now 6 cars, so I didn't updo this here. We still need to validate for vans and trucks. We checked that this is insensitive to the position of the car when it comes to the roughness measurements. Of course, the vehicle properties depends where you measure it, but there you can use different type of models, which are quarter car, which we run on the app, the half car, which we can run on a server, or full car models. That depends on the type of accuracy which we want to do. We haven't checked yet the smartphone holder. Right now, we put them we put them with a Scotch tape, with a tape to the position we want to have it in the car. So we still need to do this part of study. The excess fuel consumption, we only know that this is the state of the art right now of studies previously reported, so-called HDM4 study for the United States. So we know that we have exactly that, what this HDM4 model does for the properties of the vehicle they have used. But of course, let's say in order to validate this, we are in discussions to get access actually to the car control unit, which is not that straightforward, I can tell you. So how you can take the single measurement now to the crowdsourcing of it? Well, in fact, we have done some of these things in a complete other way for the state of California, for Virginia, for other states in the United States, where we basically had from the vehicle registration, trucks, cars amounts, or the vehicle properties, the average one, we have weight and motion data which gave us the axle load, so the weight of the mass basically of the vehicle, where we had sort of speed limit or vehicle hour delay times, where we had sort of estimates of the speeds. We had the traffic volume, climate, temperature, IRI measurements from road roughness measurements done by the agency in a very costly way, So in the forward, and then material properties, structural properties. As we use those data here, we are able actually to determine in a forward application this excess fuel consumption. It takes a little bit of big data analytics here, just to give you an idea. So this is the input here for for Caltrans state highway system. So roughly 50,000 miles, where we had the roughness measurements of the state. We had the annual average daily traffic, the truck traffic, etc., where you see important here these routes. All data here collected by the state agency, maybe every second year. So, and it's outdated often because we can only do it once they're already there. So we have no means of interfering early enough in this process here. But when we do this post-mortem, we find out that the excess fuel consumption are, of course, extremely high here around the San Francisco Bay Area, LA area, and the environmental impact is not only there big, but it's also along the truck corridors. Here you have the different quantities, not only the energy consumption, it's also the fuel. So the fuel consumption, the CO2 emissions, the NOx emission, the particulate matter, which particularly relates to diesel vehicles. Now, what we can do, and what we did with this data, is basically showing if we now have all this data, we can actually design for a state how much you need to do, what do you get out in terms of excess fuel consumption reduction if you take a certain amount of lane miles which you repair. So as you see here, if you maybe with this approach, just to maybe 20% of the roads, you actually would obtain here 60% reduction if you have all these values together. Now this is based always on historical data, but now with the smartphone, actually, we get at least a large chunk already of these values here, and could do this in real time, while obtaining also the vehicle properties without going into the database. And that's sort of the idea of the project of Fix My Road project, where we have this ambition to geographically and in time map every mile of pavement in our country for roughness, vehicle properties, excess fuel consumption, environmental economic impact, with the following objectives: to provide quantitative data for decision makers. I think decision makers, as I saw in contact with California, decision makers are extremely sensitive when it comes to the environmental impact of their communities. Not so much maybe at the federal level, but at the local level, state level, and in the cities, that for sure. Assist cities and communities to reach their climate goals. I live in Cambridge, and knowing how much excess fuel one consumes because of the road condition, it is where my kids play on the playground. And where I realized that there's a value of infrastructure for sustainable growth of our society in the city and beyond. And if we have enough people, I think there is empower citizens to contribute and take charge of our built environment. My daughter here is in the high school here in Cambridge, and she's and her classmates are enthused by this idea and want to take it on to the next level as they learn driving, measuring this directly here. So the impact here, the advantage over the current road quality measuring methods is basically you get the stuff in real time: road quality, carbon emissions, repair locations eventually, if you want to connect your vehicle properties to the repair locations, and vehicle performance. So there's all quantifiable impact. We can monitor the GHG emissions. You can individually do it, and if the data is shared, we can actually track here this year all the way to the system. And I don't know whether it will one day look like this year, but hey, this is crowdsourced, community-based infrastructure monitoring from the people, for the people, where you can basically identify for decision makers, this road needs fix it for environmental impact, if you want to reach your climate goals, from social equity of people who commute a lot, that means also a lot of environmental footprint. So this has, I believe, a good chance here to change our relationship to infrastructure. just to conclude here and leave it up here this year, so we would like to go forward with this project here. It's the first time that we speak publicly about it. We're working on this here. We have now the app here. It's right now only works on the Apple. We have contacts with someone who helps us developing the Android version of it, which not today, but if you wait until tomorrow, you get here this display of roughness and of excess fuel. Then we want to acquire data, and we're in discussions with some students here at MIT who will help us, hopefully, that the class of 2019 of MIT students actually collects the data, basically maps its environmental footprint over the spring break, over the next month. We want to move then forward here with a better version. So after all this preparations, around Labor Day, before Labor Day, we would launch the Fix My Road project, and hopefully have enough buy-in from people so that we get a representative a number of participants to map the road. With this, I would like to thank you. I hope you will join us in this effort, this Fix My Road, and I take questions. Thank you very much.
Great. Thanks so much, Franz. You've given us a lot to discuss, and we do have some questions that are coming in. As a reminder, particularly if you weren't here at the beginning, there's a Q&A box in the lower right of your screen, and if you type something in, we'll get the questions and be able to pose them to Franz and have some discussion here. So, all right, the first question is about how do you normalize for weather conditions, especially considering the extreme heating and cooling which we're experiencing more often? So I don't need, first of all, I'm not normalizing anything because I have the measurement from accelerations. If there is an impact actually of the temperature on the measurement, then crowdsourcing will clearly tell me that here that it changes. There's a seasonal change of the roughness, which I actually honestly believe that this will take place. I mean, I feel it when I take my bike to work in winter. The roads are rougher than in summer. So I think, let's say, that's something which we're going to find out as we're going to implement it. But it's all based on measurement. So the measurement of the acceleration here will actually tell us this here, as we have people participating in this venture and sharing with us the data, so we get a much better handle of the data. Remind yourself, right now the roughness is determined only by all 2 years maybe, and that only for the highway system. If you put this app on your phone, you can and share the data with us. You basically have it whenever you get into your car and measure it. So we would have the statistics then in order to see whether there is a seasonal dependent roughness and fuel consumption that results from it. Great. Another question is more about validation. Basically, so none of the plots that you showed included also data from actual IRI measurements. And so is there any plan to be able to try to, test out the validation of what you're doing with other IRI measurements?
Yeah. So absolutely. Now absolutely. This is of course part of the validation of it. So we did it for one segment actually. So the team from UMass Dartmouth actually compared it with values of the few roads where there are publicly available IRI measurements in for highways, and the values are not identical, but similar, meaning if we get 2.8 and there's as a meter per kilometer, and there it was 2.5. However, these measurements are already outdated. And you need to be aware, as every year there is an increase of roughness of the road because of the wear and tear of our system. After winter, you have an increase of the roughness here. So the data actually, the data which are available are just historic data. Now we have one plan actually of validating it in a city. We would like to have, and because there's to our knowledge, we couldn't find a direct roughness measurements for inner city application. We would like actually to have inner city roughness measurements for Mass Ave, which is the central artery here in Cambridge, which passes by MIT, in order to have here direct measurement for inner city application. I believe for highways, I think we are heads on this year. But because I don't have measurements for inner city roughness, I need here the validation. So absolutely, this is part of our plan.
Great. Another question is about a little bit more details on the IRI formulation itself, if you will. The question is, the IRI has two peaks in the gain algorithm, one associated with body bounce and the other associated with axle hop. How does the cell phone approach mimic these IRI features, considering that IRI peaks were designed to mimic the human comfort?
Okay, so I think, let's say, first of all, the IRI, I do understand this. IRI actually is the response. So the average slope of a system, a reference car, the so-called golden car, would have if it drove at 80 kilometers an hour. So, and let me just bring this back here to the quantities which are of relevance here. That means we have clearly these two peaks in the system, in the response actually of the system here. When we when we do the acceleration, you actually even have this in the acceleration power spectral density. You have these two peaks available, as you see here, with the difference here. Excuse me. With the difference that so you have here the resonant frequency and here at the higher one. So we have the similar type of profile for all the measurements for the acceleration, which of course is different than the power spectral density related to IRI. So we have this fully reproduced. What we don't have is in the actual power spectral density is this here as a fixed value because each vehicle is different. So while we have those two bumps, what we actually use in order to get IRI is we have here the part which relates to vehicle properties and the road conditions. Once you have this relationship, so this roughness power spectral density from the back analysis, the IRI is a closed form expression. Actually, we have a closed form expression developed by Arghavan and Mazdak to obtain simply from this W value and this factor here the roughness values of the system.
Great. Here's another question, kind of along some of those technical lines. For the inverse application, do you use the PSD of the acceleration, location of the phone, quarter car model? What else do you need to improve the quality of the estimation?
Yeah, that's an excellent question. So on the up, we use the golden car property because you can because it works extremely fast. We want to move by 1 second, so for updates, the quarter car model. On the server, actually, we have a half car and full car model. Now, the half car model, there are two versions of it. Actually, there are two levels of complexity. One is the left and the right wing wheel. So when you have a phone in the middle, it's a combination. It's a combination actually of the roughness sensed on the left side of the left wheel and on the right wheel. And you actually see this in the power spectral density of the acceleration, that you may have a second frequency in the system. That increases the accuracy of it. It also gives more parameters. It slows down a little bit the process, etc. So this is the half-car model, so left to right. The other one is when you want to go towards weight. So, for instance, you would like to know what is the weight of the vehicle, etc., and eventually weight distribution. Then you may need one which is the front and the back. Now, the approach here is based that we have stationary conditions and that the response are uncorrelated. Now, obviously, if you have the front and the back, for the people who are in technical one, the response of the back wheel is correlated with the front wheel with a delta T. So this complicates a little bit the analysis. They are available. If you successfully do them here, then you get mass distribution or estimates of mass distribution in the vehicle. So you can refine the type of approach. But all these approaches, if you do them in a deterministic way, are ill-posed. You have to do them in a probabilistic way. And that is the key, actually, of obtaining these results. I say this after having tried over 2 months to get it deterministically on the way, until a student of Arghavan convinced me, no way that you get there anyway.
Great. All right. Well, let's close with there's actually kind of a couple of interrelated questions that are a bit more maybe about how you use this data to inform pavement design or the design of materials that are used in the pavement. So kind of more specifically, like kind of going back to the temperatures, how do you use this information if you're planning for more extreme temperature swings? How do you take this roughness data and use it in pavement design, whether it's for asphalt or concrete? So maybe you could just close by giving us a little bit of the vision about how this, transportation agencies would use this information to help them understand deterioration of pavements and then design of materials or pavements themselves.
Yeah, so this is a fantastic question. So what I showed you right now here is one car driving at a given moment in time. Now have many car driving, not at the same time, but over different times over the same segment. What you obtain then for each one in time, you basically get the response of this particular segment here, the roughness evolution in time. That's a direct input for each segment. So that means an agency could directly realize actually that what is the value of the last repair work, which they did at this part here, in terms of the roughness increase per year, so the normalized eventually by the traffic, the type of lanes, etc. So it is this continuous monitoring, actually, having this roughness as in time and in space. That actually would that's for decision makers, for technical decision makers, it's absolutely critical to choose whether you use this overlay solution or another overlay solution, or introduce new materials which have other properties. So I think that's one point. The second one, for the design of it, of pavements for new one, I think everybody who knows the business of pavement design knows that the tools which we have are imperfect and suffer from calibration or the set of calibration. The type of approach which we here suggest actually would open up the calibration set and lead to new design tools or improve the current design tools based on the amount of data that becomes here available.
Excellent. Thanks so much. I think that's a perfect way to close. So right on time. Thanks so much, everyone, for participating in this webinar today. In case you missed it or want to share it with someone else, we're going to have it up on YouTube soon, and we'll be sharing that with the mailing list that's used for these webinars. So thanks so much, and many thanks to Franz, and we hope to catch you on the next public webinar next month. Thanks so much.
Thank you. Bye-bye.